Hi everyone, welcome back to our channel. I'm Jaden. Today we are diving into a tricky, crucial topic in the manufacturing world: how to prevent plastic parts from deforming during CNC machining. Whether you're an engineer, a designer, or just someone fascinated by the precision manufacturing, this issue is likely something you've encountered and struggled with. Before we dive into how we actually improve the deformation of plastic parts, I think it's necessary to understand the root causes behind why plastic parts are prone to deformation.
The primary cause of deformation in plastic parts is the residual stress within the material. These stresses are released during the machining process, leading to deformation. In fact, these residual stresses are formed during the production stage of the plastic materials. During the manufacturing process, when the plastic is in a melting state and cools down to solidify, it undergoes volume contraction. If the cooling rate is uneven, different areas will have varying contraction rates, resulting in internal stress. Moreover, the orientation of plastic molecules in the flow direction can also cause inconsistent contraction after cooling, further exacerbating deformation.
Now that we've identified the release of internal stresses during machining as the primary cause of deformation, what factors can influence this release?
In CNC machining, like cutting, drilling, and others exert external forces on the material. Additionally, the heat generated during milling can cause a rise in temperature. Both of these factors can accelerate the release of stress. Moreover, the choice of fixtures and the climbing methods also play a role in influencing the extent of deformation. This can cause the final dimensions to fall outside of the design tolerances, rendering the parts unstable for their intended applications. Therefore, when it comes to producing high-precision, high-demand parts using engineering plastics, it is essential for machine shops like ours to take measures to mitigate and improve the deformation issues we've discussed. Here, I'd like to use a project from 2 years ago as a real-world example to illustrate the solutions we implemented. I selected two nylon parts as examples. One is a long part with a mesh-like structure in the middle and irregular functional features at both ends. Even if made from metal, the shape would be prone to deformation during machining. The other part is circular, with an open design on one end and the minimal material connecting the center. This irregular shape is also highly susceptible to deformation during machining. Based on the material properties, we perform annealing treatment on the raw material before machining. To put it simply, we heated the sheet below its melting point, held it at that temperature for a while, and then slowly cooled it back to room temperature, ensuring the material maintains a low moisture content. When it comes to clamping, we take extra care. We use aluminum soft jaws to avoid excessive localized pressure from rigid fixtures. For the long part, we opted for 3-axis machining. After the roughing process, we perform simultaneous machining from both ends of the part. This approach prevents excessive deformation at the ends due to uneven force distribution. For the circular part, we chose a 5-axis machine. The reason is that the 5-axis machine can reduce human errors caused by flipping the part, thereby significantly enhancing the final machining accuracy. Additionally, the 5-axis machine offers more machining angles, which allows for optimized tool path and reduces issues caused by uneven tool forces. During the machining process, we let the part sit for a few hours after roughing. This resting period allows internal stresses to be released before critical precision machining begins, thereby minimizing their impact on subsequent process. Throughout the machining process, we also increase the supply of coolant to promptly remove heat from the part and maintain temperature control.
The measures we've taken before and after machining are all aimed at the controlling stress or minimizing the impact of stress release on the parts. Of course, even with through preparation and optimization, plastic parts may still gradually release stress after machining, leading to minor deformations. If this happens, we can address it with some simple post-processing corrections, such as using ways to flatten the parts or applying localized heat or adjustments.
Ultimately, both parts achieve the design tolerances set by the engineers, and the minor deformations were fully in line with their functional requirements. It was, without a doubt, a highly successful machining case.
I'm delighted to share our machining experience with you all. If you are interested in our content, please click to subscribe our channel. See you in our next video.